This is the last video where we're reviewing Chapter 1 in Algebra. We're reviewing 1.7 functions and 1.8 interpreting graphs of functions. So here I'm using our practice worksheet. You had originally been assigned the skills practice worksheet, so I'm using one that you weren't already assigned. Determine whether each solution is a function, right? So to know if something's a function, we have to look at the domain only. We're only looking at the x values. We don't care about y. So we look at the x values, and as long as none of our x numbers are being repeated or used more than once, then it is a function. If any of our x numbers are being used more than once, if they're repeated, then it is not a function. So here for number 1, we have -3, -2, 1, and 5, and they all only have one line coming from them. -3 is used with 0, -2 is used with 3, 1 is used with -2, and 5 is used with 3. So our x's are only used once, so yes, this is a function. We don't care about y's, we only care about x's. We can even mark off the y's, we don't care. We don't care about y's. Here's a table. Let's look at our x values. We have 1, -4, 7, and 1. We use the number 1 more than once. So this is not a function, no. And then for the graph, when we have a graph like this, we can use the vertical line test. So if I drew a vertical line, it should only pass through each dot, only pass through one dot, right? Vertical line here only goes through one dot. Vertical line here, only one dot. Vertical line here, only one. Here, only one. Here, only one. Here, only one. So yes, this passes the vertical line test. It is a function. If there was a spot, like let's say here, if there had been another dot, when I draw a vertical line through it, it would have crossed through 2 points. So that would not have been a function, but that didn't happen anywhere. I just came up with that. So it did end up being a function. Number 5 is a set of ordered pairs. I'm skipping around. So if we look at our x values, we have 6, 2, -4, 4, and 2. Oh, we repeat the 2's. We don't care about the second number in each ordered pair. That's a y. It can do whatever it wants. It can repeat all day long. We only care about the first number, the x values, and we use 2 twice. So no, this is not a function. We cannot repeat the x values. For y equals 2, well, okay, can I plug in an x and only get one y? I'm not sure. There is no x, right? Think about the graph of that equation. If I were to graph y equals 2 on the y-axis, I would go up 1, 2, right here, and I would draw a horizontal line, right? So would that horizontal line pass the vertical line test? Could I draw a vertical line anywhere and it only crossed through this dotted line once? Yes, that would work. So yes, this would be a function. Okay, number 9, we're going to skip down to this one. It says, if f of x, so the function of 2x minus 6, this is just y equals 2x minus 6, but we wrote it in function notation. So if this equals 2x minus 6 and g of x, just another y, equals x minus 2x squared, find each value. So for number 9, I have an f, so I'm looking just at the f of x equation, and it has a function of -1/2. So anywhere I see an x, I'm going to plug in -1/2. So that's going to equal 2 times -1/2 minus 6 instead of 2x minus 6. So 2 times -1/2, when I multiply fractions, I go straight across the top, straight across the bottom. 2 times -1 is -2. 1 times 2 is 2. -2 divided by 2 is -1 minus 6 equals -7. So that would be our answer when x equals -1/2 in this function, in this equation, y equals -7. Our solution is -7. 15, g, 3y. So this tells me I'm going to use this equation, this x minus 2x squared, and anywhere I see an x, I'm going to replace it with 3y. So I have x, so 3y, minus 2x squared. x minus 2x squared. Anywhere I see an x, I'm going to replace it with 3y. So that's 3y minus 2 times 3y squared. First, we're going to square the 3y, and then we multiply it by 2, order of operation, sorry. So 3y squared means 3y times 3y, which is 9y. So this whole thing becomes 9y, and then we multiply 2 times 9y, which is, 9y squared. And then we multiply 2 times 9y squared, which is 18y squared. And we can't simplify it any more than that. So using g of x equals x minus 2x squared, if I plug 3y in for x, I get 3y minus 2 times 3y squared. And I simplify to get 3y minus 18y squared, and I'm done. This is my solution. I can't solve completely because I don't know what y is. Okay, then the word problem here, number 17. Martin earns $7.50 per hour proofreading ads at a local newspaper. His weekly wage, W, can be described by the equation, his weekly wage equals 7.5 times the number of hours he works, where H is the number of hours. A, write the equation in function notation. Okay, so wages is a function of the number of hours he works. The wages depend on the number of hours he works. So I'm going to write W of H equals 7.5H. I'm using W because that's our thing here. You know how they use like F or G up top. I'm using W because we're kind of talking about wages. But wages is a function of the number of hours worked. Like I said, wages depend on the number of hours worked. Okay, find F of 15, F of 20, and F of 25. So this is our F, right? It's the same thing. Find W of 15, W of 20, and W of 25. Okay, so the first thing, 15, would be 7.5 times 15. 7.5 times 15, if I use my calculator, is $112.50. So when he works 15 hours, he makes $112.50. When he works 20 hours, 7.5 times 20, $150. He makes $150 when he works 20 hours. And when he works 25 hours, what do you think he'll make? We went up there in 5 hours, we went up from $112.50 to $150. So 7.5 times 25 equals, $187.50. Not bad for proofreading, right? So 15 hours, he made $112.50. 20 hours, he made $150. 25 hours, he made $187.50. And then for the sake of time, we're going to stop there. So hopefully that helps you with determining whether a relation is a function and then writing an equation in function notation. And just to reiterate that, a regular equation would be y equals, let's say, 4x plus 10. Let's just say, for an example. Y, whatever y is the dependent variable. It depends on what number we put in for x. So essentially, y is a function of x. So even though we write it different, this is function notation, it's still y. It's still a different number. This output depends on what we put in for this number. So it's y, but it depends on x, so it's a function of x. So that's why we write it this way. This is function notation. Okay, and then 1.8, interpreting graphs of functions. So I kind of pre-wrote what we have to look at here. Basically, as long as you understand what a graph is showing, you are good. The other stuff is nitpicky, right? And yes, you need to know what each of them mean, but at the end of the day, it's such a small part of everything you need to know in algebra. I wouldn't stress over it if it's totally confusing you, okay? So for this graph, we have weeks along the bottom, 2, 4, 6, 8, 10, and we have Is that savings in dollars along the top? And that's $1,200, $1,400, $1,600, $1,800. So it looks like at 0 weeks here, at the very beginning, we start off with $1,400, $1,400. And then as the weeks pass, we go up at a steady rate. We increase at a steady rate. As long as you understand that, you're good to go. All right, so let's get into the nuts and bolts of it here. Is this a linear graph or a nonlinear graph? Is it a straight line or not? It is a straight line, so it's linear. Where does our graph, what we can see, cross the x-axis? It doesn't. There is none. We never are at $0. We open the savings account with $1,400 right here, and then we just increase the amount in the account from there. We're never at 0. We're never on the x-axis. We never cross it. So there is none. Where do we cross the y-intercept? When time is at 0, what is our y amount here? It's 1,400. So 0, 1,400. Meaning we open the account with $1,400 in it. Is there any line symmetry? Can I draw a vertical line anywhere and fold my graph in half and it match up? No. Our graph would have to look like a V for us to be able to fold it in half and it match up. If we folded it in half here, one side would go up and then this side goes down. So there is no line symmetry. Where is our graph positive? Where is our graph above? Where is our graphed line above the x-axis? Positive and negative, think of the x-axis like water level. If you're above water level, you're positive. If you're below water level, you can't breathe, and that's negative, right? So what part of our x-axis is our graph above? Looks like the entire thing, starting off at 0. So as long as x is greater than 0, as long as it's anything bigger than 0, and it could be actually equal to 0 as well, our graph is positive. So x can be greater than or equal to 0, and our graph is above the x-axis. Anywhere our graph is below the x-axis, no, everything's above, so there is none. All right, where is our graph going up? When we read our graph from left to right, where is it increasing? Well, the entire thing is increasing, right? And it's time along the bottom, so there is no negative time. So our graph starts at 0 when x is 0, and then it goes up from there. And the entire graph, as long as x is bigger than 0, is increasing. So as long as x is greater than 0, our graph is increasing. When we're measuring all this stuff, we're measuring it in portions of the x-axis. When we look at our x-axis, what's our graph doing up and down? Okay, decreasing. Anywhere our graph is going down? Nope, none. All right, then we have minimums and maximums. These only occur, the relative extrema, the relative minimum, relative maximum, when our graph changes direction. So if it was increasing and then it decreased, or if it was decreasing and it increased, then we would have a relative minimum or maximum. Here it doesn't change direction, so there is no minimum or maximum. Only when we change direction. And then the last part is end behavior. So for end behavior of a graph, you're only going to have two things, right? We're going to look at what our graph does as x gets bigger and what our graph does as x gets smaller. That's it. So as x goes up, what does our graph do along the y-axis? As x gets bigger, our end behavior here of our graph is getting larger. So as x gets bigger, our graph goes up along the y-axis. And as x gets smaller, as we're looking at it to the left, what does our graph do? It looks like it's going down. If I was here and I look to the left and my graph is getting smaller, my x's are getting smaller, my graph is going down. So the y value is getting smaller. That's all I got to know for end behavior. What's it doing on the right side? What's it doing on the left side? As x goes up, as I go to the right, my graph goes up. As x goes down, as I go to the left, my graph goes down. Okay, we're going to do one more just like that. We're looking at the exact same things. So this graph looks a little different. It is not a straight line. So this graph is non-linear. Where does it look like it crosses my x-axis? Well, it looks like it crosses it here and here. So my x-intercepts are at 0, 0, and 120, 0. Before we go any further, what is this graph showing? It says it's the height of a golf ball. So distance from the tee, distance from the little thing you hit the golf ball off of in yards, this is this measure, and then the height of the golf ball here. So as you get further and further from the tee, the height of the golf ball goes up, right? Distance from the tee, height of the golf ball. Makes sense, right? All right, so y-intercept. Where does my graph cross my y-axis? Looks like 0, 0. All right, line symmetry. Is there anywhere I can draw a vertical line, fold my graph in half, and it matches up? Yes. It looks like right about here. We're just kind of estimating. This isn't perfect. But it looks like if I folded my graph in half here along this axis, both sides would meet up perfectly. So this looks like it's about when x equals 60. So yes. And our line, our vertical line, is when x equals 60. If we folded our graph in half at 60 along the x-axis, both sides would match up. Looks like pretty much perfectly. All right, where is our graph above the x-axis? Where is it positive? Well, it looks like it's positive anywhere between 0 and 120, right? Anywhere between here. So when x is between 0 and 120, our graph is above the x-axis. So x has to be less than 120, but greater than 0. Okay, where is our graph negative? Where does it go below the x-axis? Well, distance from the tee, we can't be negative. Time and distance can never be negative. So x can't be low. It looks like as we go down here, as x gets smaller, our graph goes negative. But x can't get smaller. It starts at 0. But what about when x gets bigger than 120? Where's our graph going? It looks like, since it touches 120 here, that it goes below the graph here. So if x is anything bigger than 120, our line goes below the x-axis. So when x is greater than 120, our graphed line goes below. It's negative. It's below the x-axis. Where is our graph going up when we read it from left to right? Where is it increasing? It's increasing when x is between, what portion of our graph is it increasing? When x is between 0 and 60, this line of symmetry here. When x is in between those two numbers, when we're in this portion of our graph is going up, right? So when x is in between 0 and 120, it's greater than 0 and less, sorry, not 120, 60. When x is in between 0 and 60, if we find our graph in between 0 and 60, our graph is increasing. Then if we look at our graph between 60 and 120, or 60 and bigger, it's decreasing, right? Anything, when our graph is anywhere bigger than 60 on the x-axis, our line, our graph line, is going down. So when x is greater than 60, our line is decreasing. Relative minimum and maximum, I told you that only happens when we change direction. Did we change direction here? Yeah, we just talked about it. We were increasing until we got to here, and then we started decreasing. So where is this point? About. Where is this highest point? Well, it looks like it's over 60 and up. If this number is 140, then this would be about 150, I would say. It's halfway in between these two lines. This line's 140, this is 160, so we'll say about 150. So over 60, up 150. 60, 150. And that's the highest point we got to. We went up, we changed direction, we went down. That's the highest point we got to, so that's a relative maximum. And there is no other direction change, so there is no relative minimum. Okay, if we were riding a roller coaster, you're going up, 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 up. This is the highest point you get to, and then you go down. There's no point where we're going down and we bottom out and go back up. That would be a relative minimum. We don't have that here. All right, and then last, in behavior. So look at the two ends of our graph. As x gets bigger, what's our graph line doing? It's going down. So as we go to the right, our graph goes down. And as we go to the left, our graph is going down. As x gets smaller, our graph is getting lower. Right? So that's how we interpret graphs. Don't read too much into it. If you are way confused, don't worry about it. If you're kind of getting the gist of it, that's all I expect here. Let me know if you have questions.